So you've built a model, you've trained it, and the accuracy on your training data is almost perfect. You're feeling pretty good, ready to ship it. And then you test it on real world data, and it just completely falls apart. It's a classic, and honestly, a really frustrating moment that pretty much everyone in this field goes through. This leads to the big question we're going to tackle today. Why does this happen? Why can a model that seems so brilliant on the data it has seen fails so badly on data it hasn't? Well, the answer lies in finding a model that isn't too simple and isn't too complex, but is, you guessed it, just right. By the end of this explainer, you'll understand exactly how to solve this Goldilocks conundrum of machine learning. Here's how we'll break it down. We'll start with the core dilemma that every model faces. Then we'll look at the two extremes, being too simple, which is underfitting, and being too complex, which is overfitting. We'll connect this to a really important idea called the bias-variance trade-off. And finally, we'll look at how we actually find that balanced, just right fit. You see, the fundamental challenge in machine learning isn't just about getting the right answers on data we've already seen. The real goal, the whole point, is to build a model that can generalize, to make accurate predictions on new data it's never encountered before. Let's look at the first extreme. Imagine a lazy student who barely even glances at the textbook before a big test. They don't learn the underlying concepts, so of course, they do poorly. A model can be like this too. We call this underfitting. It's just too simple to grasp the basic patterns in the data it's given. Formally, underfitting happens when a model is just too simple and completely fails to capture the underlying data patterns. Because it consistently learns the wrong thing, we say this results in high bias. Think of it like this. If you were trying to separate sick trees from healthy ones in a forest, an underfit model might just try to draw a single straight line between them. It's an overly simple approach that's going to misclassify a lot of trees, even the ones it's already seen. Now let's look at the other extreme, overfitting. This is like the overzealous student who doesn't just learn the material. They memorize every single question and answer from the practice test down to the last comma. The problem? When the real test has slightly different questions, they're completely lost. This happens when a model matches the training data too closely. It doesn't just learn the pattern, it starts memorizing the noise and all the random fluctuations. This means it fails to generalize, and we say it has high variance. It's way too sensitive to the specific training examples it saw. An overfit model creates a boundary that's way too specific. Instead of a simple curve, imagine a crazy, squiggly line that perfectly weaves around every single data point it was trained on. It gets 100% accuracy on the training data, sure, but it's memorized the noise, not the true pattern. It will almost certainly fail when it sees a new tree. So we have these two opposing problems, underfitting and overfitting. The technical concept that connects them is the bias versus variance trade-off. And this is truly one of the most fundamental tensions in building any model. Let's just put them side by side. Underfitting models are too simple, leading to high bias and poor performance everywhere. Overfitting models are too complex, leading to high variance. They look amazing on training data but are poor on new data. And notice the key result. In both cases, the model is not useful in the real world. This brings us to the trade-off itself. As you make a model more complex, its bias tends to go down, which is good. But at the same time, its variance tends to go up, which is bad. The goal is always to find that sweet spot, the level of complexity that minimizes the total error by striking the perfect balance between the two. So in practice, how do we find this sweet spot? We use a validation data set. While we're training, we monitor the model's error, or loss, on both the training data and this validation data. A huge signal of overfitting is when the training loss keeps going down, but the validation loss bottoms out and starts to rise. That divergence is the classic sign that your model has stopped generalizing and has started just memorizing. Okay, so knowing the problem and how to spot it is half the battle. Now, let's talk about the practical techniques we can use to build a model with that just right fit. The ideal model finds that middle ground. It's not an oversimplified straight line, and it's not a chaotic line that memorizes every single point. A good model learns the underlying pattern, creating a smooth, generalized boundary that performs well on data it's never seen before. As practitioners, we have a whole toolkit for this. To fix underfitting, we might need to add more features to let the model learn more. To fix overfitting, we can do things like feature selection to simplify it, or use a really common technique called regularization, which adds a penalty for complexity. Other powerful tools include ensemble methods like random forests, which combine many models, and cross-validation to get a really reliable estimate of how your model will perform. Ultimately, this all comes back to a core philosophy of machine learning. The goal is not to create a perfect model with 100% accuracy on the training set, but to create a useful one that actually generalizes to the real world. So your key takeaway is this: always be skeptical of a model that looks perfect in training. The essential question isn't how high can I get my score, but how much complexity is truly necessary to solve this problem. That is the path to building a robust model.